after defining abstractly what the dimension of a topological space is, we now want to consider how, for the affine varieties that we're looking at, can we compute the dimension. And we want to apply results from commutative algebra. And we do this by applying these results to the ring of functions. It turns out that this knows about the dimension. And for applying this, we want to recall some definitions from commutative algebra, which say that given a ring R, the Krull dimension of R is the supremum of all numbers n, such that inside R we find a chain of prime ideals, P0, P1, P2, and so on, up to Pn, which are all strictly contained in each other in this way. And then similarly, if you're given any prime ideal P, then the height, or also called codimension of P, is the corresponding supremum of length of chains, very similar to the thing above, except that they must end already in this prime ideal P. Okay, these were the definitions. And then the lemma that we start with is saying that assume you have an affine variety X, and then Y inside X, a non-empty and irreducible subvariety. Then the claim is that the dimension of X equals the Krull dimension of its ring of functions AX. And similarly, the codimension of Y inside X equals the height of the ideal of Y in the coordinate ring of X. In particular, these two numbers are finite, because last time we have seen that even though, even when you assume that X is an Noetherian topological space, like for affine varieties, this does not guarantee that it has finite dimension. But here we see for all these affine varieties we look at, this dimension will always be finite. And the proof is pretty short because, well, we have by the Nullstellensatz again, this time the relative variant, we have a correspondence between irreducible subvarieties of X and prime ideals of its coordinate ring. And then the dimension, like for part A, the dimension of X was defined in terms of a supremum of length of irreducible subvarieties of X. And then any such chain goes one-to-one to a chain of prime ideals. The inclusions reverse, but the length stays the same. And so this is basically, so part A is just a translation of the definition in terms of irreducible subvarieties to the definition in terms of prime ideals for the Krull dimension of AX. And similarly, we have that for the codimension here, the chain of irreducible subvarieties in X had to start with Y. And if you do the correspondence again, then the chain of prime ideals must terminate in the ideal of Y, which is the prime ideal that we apply this here too. So this also proves part B. And then for the finiteness, we simply observe that A of X is a finitely generated K algebra because it's the quotient of the ambient polynomial ring by the ideal of X. And the ambient polynomial ring has finite Krull dimension, and then a quotient of something like this also has finite Krull dimension. And I mean, to see that, you can just think about like what were the prime ideals of the quotient. They're just the prime ideals of the original thing containing the ideal you mod out. So you have kind of at most as many prime ideals to compute the Krull dimension of a quotient as you have for computing the Krull dimension of the original thing. Okay. This was a basic lemma, and this tells us if we're interested in this dimension, we can just look at the coordinate ring and use all the results we have about the Krull dimension. To start with some examples, so the most basic affine varieties are the affine space AN And it turns out there the dimension is exactly n, because, well, if you look at the ring of functions, this is just this polynomial ring, and we have seen in the lecture last year that the Kroll dimension of this polynomial ring is n. And this can be evidenced by such a chain of prime ideals. You start with a maximal ideal associated to just all of the variables, and then you can remove one variable at a time. All of these things are still prime ideals. All of these things are contained as explained, and they're strict containments. And so you see this is a chain of length n. There's n different inclusions here. This would show that the Kroll dimension of this ring is at least n, and then you can also show the other inequality. And second of all, we consider a very concrete example, something which we have already seen a couple of times, this vanishing set of y minus x squared. This looks like this. And then its coordinate ring is this quotient here. And then we already saw we can use this ideal to eliminate the variable y. And so the quotient ring is actually just isomorphic to k of x. And then by this result here, we see that this is one-dimensional. And this kind of fits with the picture, because here the ambient space A2 is two-dimensional when we have a single equation. And in the real picture, I mean, it really looks like a curve, a one-dimensional real thing. So everything makes sense so far. And these were some examples. And next we want to basically transfer like all results, which we know from commutative algebra about the Kroll dimension, to results about dimensions of affine varieties. And that's one of these instances, like once you make a connection between the algebraic side and the commutative algebra side, and of a whole host of results from the commutative algebra just gets translated for free into results on the algebraic geometry. Okay, and so here is the proposition, some properties of dimension. And the input is that we fix x and y to be non-empty and irreducible affine varieties for now. And the first claim is the dimension of their product is the sum of the dimensions, where this product is the affine variety which carries the corresponding Zariski topology from sitting in the product of the ambient affine spaces of these two. And as a side remark, this is the second way to show the dimension of a to the n is equal to n, because we could kind of see by hand that the dimension of a1 is equal to 1, just because we basically can write down all of the prime ideals. And then, well, an is the product of a1 cross a1 cross a1 n times. And so its dimension, applying this a couple of times, is just the sum of n summons equal to 1. So this is n. Okay, that's another way to see this. Then secondly, there should be a relation between dimensions and codimensions. So if y is a subvariety of x, then we have the dimension of the big thing is equal to the dimension of the subvariety plus the codimension of the subvariety. And so this kind of makes sense, because the codimension should be kind of the deficit of the dimension of y inside x. And in particular, if you like, if you choose y to be a singleton set, so a single element contained in y point, then the codimension of this is equal to the dimension of x. To see this, you just have to observe that the dimension of this y is equal to 0. And that is, again, very easy to see from the definition, because, well, it's just a single element set. So the only chain of irreducible subsets is just the chain of length 0 formed by this single set. Okay. And then finally, if you have a single function f in a of x, which is non-zero, then every irreducible component of its vanishing locus has codimension exactly 1 in X. And in particular, this vanishing locus has dimension dim X minus 1. So the idea behind this is if X has a certain dimension and then you impose one condition, one vanishing, so impose a single equation, then you would expect the dimension should drop by 1, you lose 1 degree of freedom, and this third part of the proposition makes this precise. And so for the proof, we now need to kind of dig up the results from commutative algebra. So for part A, we want to understand the product of two varieties. And what we have already seen in one of the earlier videos is that the ring of functions on here is the tensor product of the corresponding rings of functions on X and Y. So we want to show the dimension of this tensor product is the sum of the dimensions. Now this looks again like it might be a fully general statement, which holds for very general rings, but that is not correct. So there's examples where this doesn't hold as nicely. And the correct generality in our case is that if you have R and S, two finitely generated algebras over the field K, and you also assume that R and S are domains, integral domains, then the dimension of this tensor product here is the dimension of R plus the dimension of S, where this is now the Krull dimension. And at least we see if we have this lemma, we can finish the proof because indeed AX and AY are finitely generated algebras, and there are domains because we have assumed X and Y to be irreducible. So the lemma, I will not give the full proof of the lemma, but just as a kind of idea what goes into there. Well, if n is dimension of R, m is the dimension of S, then you can apply this Noether normalization lemma, and then you find an injection from this ring of polynomials in n variables into R, and the ring in m variables into S, such that R is a finitely generated module over this, and similarly for S. And so somehow the Krull dimension can always be computed in terms of such a Noether normalization. And then what you check is that, well, there's basically a map. So somehow you have two maps of rings. They're both maps of K algebras. And so you can now take the tensor product of the domain. So the tensor product of these two things is just the polynomial ring in the union of the variables. And it maps to the tensor product of R and S. And then one thing you should check is that this is an injection. So here, I mean, with tensor product, injections are not necessarily preserved, but the fact that we're working over a field tells you that nothing goes wrong here. And then you show it's also kind of the target is a finitely generated module over the domain. And this together with this characterization allows you to see that this has dimension n plus m, I guess. Sorry, it should be m. Okay, so this is one thing. We have proven the first part. For the second part, B, this uses a nice result, which says that in such a ring AX, all maximal chains of prime ideals have the same length. So this means that if you have any chain of prime ideals which computes the Krull dimension of X, so this would have such a length here, then it would always have length dim of X. And then what you do is you first look at Y and then choose the length, a length dim Y collection of prime ideals inside AX, which uses here the fact that, well, the dimension of Y is equal to the Krull dimension of A of Y. But A of Y is isomorphic to A of X modulo the ideal of Y. And then whenever you have such a length of such a chain of ideals inside A of Y, the preimage in A of X gives you a corresponding chain of prime ideals in A of X. So this is the one part, and then the codimension of X and Y, sorry, of Y and X. This is the length of some chain of prime ideals which end in P of Y. And then this is a maximal chain. It cannot be extended by adding any further prime ideals. Otherwise, either this chain or this chain wouldn't have had maximal length. And so then this gives you a whole chain of prime ideals inside AX, which have the maximal length. And this gives you dimension of X. And then you basically just see this length plus this length is the entire length. Okay. So this was part B, showing that these kind of dimensional codimensions add up. And then the final thing about this single equation F, which cuts out V of F. Well, the fact that that this has codimension 1 in here means that the ideal generated by every single ideal of an irreducible component of this Vx of F has codimension 1, and then we observe the components of this vanishing locus that we have seen before correspond to the minimal primes in this quotient ring. So these are somehow minimal primes in the quotient ring, and this is the same thing, again, using this relation between prime ideals of the quotient. These are also the same thing as minimal prime ideals of A of X containing this. And then it's exactly Kroll's principal ideal theorem, which tell you that all of these things have height 1 or codimension 1 inside A of X. So we have seen that sometimes with some extra arguments, we could transfer results about the Kroll dimension to the geometric setting and get results about dimensions of affine varieties.